So hello students, today is my first video. As the time goes on, I will put some more videos on topic like electrodynamics, mathematical physics, classical mechanics, solid state, nuclear and particle physics. All the subjects that are related to CSIR, NET, GATE, TIFR, JEST, etc. and some other advanced topics also, that is a plus MSc topics. So I will start this video, and here is my first slide. As you can see, the topic, that is derivation of Schrodinger equation and particle in a box. But at the later point, I will show you that you can't actually derive Schrodinger equation, you can only postulate it. So I will come up with this point, but let's start. So okay, by starting my video, I will briefly describe about how to describe the motion of a particle with some momentum p and energy E, and this equation which you are seeing in first equation, it is basically all you know. This is from electrodynamics. If you have studied electrodynamics, simple plane wave equations, then this is the equation we come up with. The equation which you have seen is like that. What I say that you have seen this equation in this form. Like if I tell you the equation 1, I can show you that you can basically what you have seen, that is some psi xt is equal to some a e I kx minus omega t. In this form, we have seen this equation of a plane wave equation in electrodynamics. When you study Maxwell equations, then we have seen this type of equation. What I have done, I have convert it to momentum p and energy E with the help of E is equal to h cut omega and p is equal to h cut k, where omega is your angular frequency, E is your energy, and k is your wave number. Now the point is, I have written this first equation in 3 dimensions. Now equation 2 is only in plus x direction, that is a plus positive direction, plus x direction. Okay, so equation 2 is just the Fourier transformation. If anybody don't know about the Fourier transformation, I've written the general formula for Fourier transformation, and basically when I will put the mathematical physics lectures, then you will come up with this Fourier transformation. But I will show you the general equation. So the general equation is this Fourier transformation. In general, Fourier transformation of fx is any function. If you will do Fourier transformation, then you come up with 1 upon under root 2 pi integrate between minus infinity to infinity. Minus infinity to infinity is the whole space. You have taken the whole space and you have to integrate it. Fx is the given function and exponential e raised to ikx dx. Okay, so this is the general Fourier transformation formula, and when you put it, so using general transformation, we can construct this psi x comma t is equal to 1 upon under root 2 pi minus infinity to infinity phi k e ikx minus omega t dk. Okay, so I've shown you this, how we came up with this. Now let's come up with this our previous slide. So here k is equal to p upon h cut, and you put the various values I have given here, and we will go to that equation number 3. Okay, equation number 3. Now see, if equation number 3, you'll see this is basically when you put the values is equal to h cut omega, p is equal to h cut k, and all this, you come up with equation 3, and it's very easy. You can do it. Just you have to put the values, and here phi p is the momentum amplitude. So see, now question arises, can we derive Rayleigh's Schrodinger equation from the principles of from the first principles we know? The answer is no. You can only postulate it. See, in my later videos, I will come up with the postulate of quantum mechanics. In this one postulate, time evolution postulate, you have studied this postulate, this H psi is equal to E psi. H is equal to the Hamiltonian, which describes the total energy P square by 2m plus V. V is potential and P square by 2m plus is kinetic energy, and E is, and in right hand side E is equal to E psi. E is your that is energy operator. Is both has dimensions of energy, H psi and also E psi. So now see, basically the point is, you can't derive Schrodinger equation of the first principles, only you can postulate it. And now the question arises, how you know that that the postulate you have chosen, or the postulate you have given, are correct. See, you can't postulate you can't test directly. Okay, what you can test is the when the results come up with this from postulates, you can test it. One can go in laboratory or any other method and can check that results are correct. If results are correct, then automatically postulates are also correct. Like see, in special theory of relativity, when Einstein came up with special theory of relativity is equal to mc square and time dilation and various concepts. At that time, he postulated two postulate, that is speed of light is constant. The speed of light is constant is a postulate. One cannot at one can test it indirectly, but this is not a direct method. At the time of Einstein, he have not tested. This is a postulate, and he taken up from the Maxwell equations. So when you study Maxwell equations, then we study C is equal to 1 upon under root mu naught and epsilon naught. So I have completely gone out of the track of the topic. So let's come with this slide. So basically my point is that you can't derive it. What I will show, that I give you a recipe or one starting point where you can start with this and end up with Schrodinger equation. Basically, this is not derivation. This is how you come up with Schrodinger equation, and how actually Schrodinger came up with this. This is an educated guess. What he started from this equation number 4. The equation number 4 is nothing but equation number, I have rewrite equation number 3, and from where we have seen E, I have written E is equal to P square by 2m plus V. I can show you this. Yeah, here you can see I have highlighted is also with green and this color highlighter, where E is equal to P square by 2m plus V is your total energy, P square by 2m is kinetic energy, and V is your potential. Okay, so equation number 4 is from this. Okay, now I will show that how you can go from equation 4 and come up with equation 5. See, equation when you will see, this is your equation number 4, and I have written a partial. When you do the partial time derivative of equation number 4, okay, the factor of I h cut is to just do it dimensionally correct, and when you do the time derivative, here the constant is outside, minus s square by 2m curly square by curly x square plus v is the constant outside, and you come up with this equation number 5. And basically this integration 1 by under root 2 pi h minus infinity to infinity, you can see that it is your previous equation 4th psi xt. So I can directly write psi xt here. I can show you again. See, this integration minus infinity to infinity is psi, just the psi xt part. So I've written psi xt here, and this the equation with green highlight time, this is your time dependent Schrodinger equation. Okay, so you come up with equation number 6. Now the question arises, how one can come up with time independent equation. Time independent equation, like see, here we have chosen the the potential that is time dependent. If we choose time independent potential, so the Hamilton operator will also be the time independent, and hence the Schrodinger equation will have two solutions that are separable solutions. One depend only on r and one only on time. If you don't know the seventh, how come I with 7? This is just the I will show in some other video that how can we do this, but this is the you can take it as granted. This is the another proof we can do, or you can do as exercise. So this by equation 7, this is time independent. So time independent Hamiltonian, we can write this in two solutions, like one is dependent on r and one is on time. Okay, so this is equation number 7. Now we come up with equation number 8. I have rewrite this equation number 6 to equation number 8 in 3 dimensions. It is just in 3 dimensions, nothing else. Now if I substitute this equation number 7 into 8, what I am saying, that see, this is psi r psi f t, and this is your equation number 8. Now what you will do, if you substitute psi r t psi r f t in this equation, in equation number 8, then and divide the whole term by psi r f t, then see, I have done this as iota h cut psi r curly ft by curly t, and you have divided by psi r f t is equal to minus s, and all this when you will do, you will get this this equation, and I have this written this equation is equal to E. This is a constant and dimensions of energy, and from this we can write two differential equations. One I have highlighted with green, iota h, this is time dependent, time equation, and this is one is a radial equation, that is only a wave function. Okay, so you have come up with two equations, one highlighted above and one highlighted with green below. Okay, so here you come up with, so the part which you have those, so the 11th equation which you have come up with this two separable solutions, and one that is one is of psi r, this is actually the time independent Schrodinger equation, and this is time independent Schrodinger equation. So this is your and this is the fact, and ultimately we have come up with time dependent Schrodinger equation and time independent Schrodinger equation. Now I can show you some other information that I have not written in this slide, but see, the one equation which I have marked with star, that is your time that is time independent equation, that time solution. The solution to star is ft. This is simply the differential equation, and if you don't know that how the solution comes, you have to study the differential equations, and it is very easy. And if you don't know, take it as granted in this, and in my other videos when I will put up the lecture of differential equations, then we can study in detail that how this that I've written with this blue, the solution to star is that how this solution come up with. And hence like psi rt is equal to psi rft, that is the two separable solutions, and we can write f bracket t with e raised to power minus I et by h. Okay, the solution and the solution of star. Okay, we can put it in this f function of t. This particular solution of Schrodinger equation for time independent is called stationary state. Why this is called stationary state, I've written in this green. You can see that if I take the mod or I take the square of this, ultimately when you will do square, that e raised to an imaginary term will come up with e plus, and it will cancel each other, and basically what you come up with only psi r. Basically what it means, that what is stationary state, that the probability density is stationary, that is does not change with time, or you can say it is constant, it does not change up with time. So this is the equation, that's why we call it stationary state solution, because it does not depend upon time when we take the probability density of this equation. So this is called a stationary state solution, and it is very important as it uh, as you will get many questions on this part what I'm here teaching, that's Schrödinger equation. uh, uh, every alternative years or two after 2 years, the question in net you can see on this part, h psi is equal to e psi. You can state it. Now sorry so now we will come to the particle in a box or width 2a. Why I will taken the width 2a? This is a symmetrical this is a actually the symmetrical box. This is not asymmetric. If you have to take a symmetric, then you can take the width from 0 to a, but it is 2a. And how is it 2a? Like I've shown in this, you can see minus a to a. So if you will take the width, that is a minus minus a, it will become 2a. So the width is 2a. So this is symmetric potential well, okay, with infinite walls. So and in you can see the condition of potential is 0 from minus a to a. Minus a to a, it is 0, and when otherwise it is infinity. When it is less than minus and or is greater than a, it is infinity. So and psi is equal to 0, that is probability probability is equal to 0 at the walls. From the time independent Schrödinger equation 1 is only the time independent Schrödinger equation. If you don't know, I can write it how the equation 1, how can we write equation 1. This is just the time independent Schrödinger equation. We have written in this form. So this is the equation. Here v is equal to 0, so you come up with 2me by here v is equal to 0, so you come up with so here we have done I solved it. So this is the equation number 1. Okay, so now equation number 2. The solution of this one is given by a sin kx plus b cos x. Again, this is the differential equation. You come up with complementary function, particular integral, you will get it. So only you have to do complementary function, not particular integral. So you come up with this equation number 2. If you don't know, then you have to take it as granted, and we will do it in upcoming videos. Okay, so you have seen the diagram properly. What this diagram I will come up with this later on the diagram part, but basically you have to see that in the interior region v is equal to 0 and outside v is equal to, that potential is equal to infinite. This is the starting point. We have to take it, and in the next slide we will go. So here if you apply the boundary conditions, now we have chosen the boundary conditions, and with boundary conditions that at x is equal to plus a and minus a, psi, and I've told you that psi is equal to 0. So applying these boundary conditions from equation 2, we can get this equation number 3 and equation number 4. Basically, you know that sine is an odd function and cos is an even function. That's why in equation 4 it is of minus sine of minus theta is equal to minus sine theta, and cos of minus theta is equal to cos theta. So you come up with equation number 3 and equation number 4. By simultaneously adding and subtracting equation number 3 and 4, you will get equation number 5, that is b cos k is equal to 0 and a sin k is equal to 0. Now if you put a is equal to 0, b is equal to 0, you will not get anything. That psi is equal to 0 and is unphysical solution. basically there should be some probability. So what we can do, at one point of time we can do a is equal to 0 and b is not equal to 0, and another point we can do a is not equal to 0 and b is equal to 0. So the first condition gives cos k is equal to 0 from k. Now you know that the cos theta is 0 at n pi by 2. That is your cos 90, and on value n is equal to 1, 3, 5, 3 pi by 2, 5 pi by 2, pi by 2, cos is 0. From here you will get k square is equal to 2me by h cut square. So for this come up with this, like k square we have assumed it 2me by h cut square. So you can go with here, and from here you can get by if k square is equal to n square pi square upon 4a square. Okay, this is equation number 6. And now equation number 6 you got. Now on the next slide we will move, and we will see that the energy from here we will get pi square h cut square n square upon 8ma square, and it is only for you can at this time you can say it is only for n is equal to 1, 3, 5 and 7 odd numbers. And on equation number 8, the corresponding eigenfunction to this eigenvalue, if I choose, then you can see that it is b cos n pi by x. What I can do this, what I can show you that this you can put in this equation. You will get that part of the wave function. You can put in this part, you can put here, and you will get the wave function part. In equation number 2 you can put this. Okay, in equation number 2 you can put and you will get this this part. You will get psi x is equal to b cos n pi x by 2a. Like I can show you that here we can get a is equal to 0. So a is equal to 0, you will only remain with this that b cos k x. You can put the value of k, and you will can get this b cos n pi x by 2a. Similarly, using the second condition of n is second condition. What is second condition? Second condition is this, like that a sin k is equal to 0. If you put this, then you will get this equation number 9. And similarly, if you will solve the eigenfunction of this particular eigenvalue by b is equal to 0, a sin k, b is equal to 0, the second term will be 0, and psi is equal to a sin k, and put the value of k, you will get this equation number 10. And you will see that the energy is same, but the eigenfunctions are different for when you will take the odd quantum numbers, and different for when you will get for that even numbers. This is the case for symmetric. See, for the case of symmetric symmetrical box or symmetric potential well, you will get the two eigenfunctions, one for odd quantum numbers and one for even. But if you solve the S metric, that is 0 to a or 0 to L, you will get only one eigenfunction. Okay, so this is the important. So this can you take an exercise to do it for 0 to a or 0 to L, or you can do 0 to a pi by 2. So this is, you can take as an exercise, and you get only one eigenfunction, and with respect to that an eigenvalue. So I want to discuss some here points, like you can see equation number 7. Here E is energy, pi is your pi, and h cut is your reduced Planck's value, and m is the mass. Okay, and a, see here, a is the width. So if I have chosen minus a to a, so the width is 2a. If I have chosen like minus 2a to 2a, then it will become 4a. So there you have to write a is equal to 4a whole square, and in equation number 8 you have to do it 4a. So accordingly the width will change. This is very important concept which you will get in CSNet questions also, like, and they will change the width and ask you the particular eigenfunction or eigenvalue. Then the most students do mistake here only, that they do not change the width. So width is a, you have to change it accordingly as it is given in the question. So equation so next slide, some important points we can say. So if we come up with some important points, here we can see the quantum number n is equal to 0 is not included, as it corresponds to the trivial solution. Like n is equal to 0 is in accordance with the 0 point energy. You can say there is some energy, you can't take it n is equal to 0. I will discuss about what is the that is 0 point energy in next slide, but this in accordance with uncertainty principle, that is the minimum uncertainty or minimum energy is there, that if n is equal to 0 is there, then psi will equal to 0, then the probability of finding the particle will be 0 in whole space. Like there is no particle in the box, which can't be possible. So there is something minimum energy. So minimum energy is n equal to 1. So I will discuss it later, but here we will discuss after normalizing the equation number, that previous eigenfunctions, you will get 1 by under root a sine n pi x by 2a. And I hope everybody know how to normalize function, that is your integrate psi star psi is equal to 1. You will put psi star is your conjugate and psi is your given function. When you will do equal and you will do it equal to 1, you will get the normalization constant, that is 1 upon under root a, and you can do it as an exercise for this function. I also tell you something, like you can do it directly also, something like see, if this is the 0 to a, so this is asymmetric, so width is equal to a. So here width is equal to a and v equal to 0 here. So for this the eigenfunction is under root 2 by a sine n pi x by a. Here n is equal to 1 2 3 4, and so what I have done in this, that is in the previous slide I have chosen minus a to a. So what you can do, you can directly change it. Psi is equal to under root, width is now is 2a, so I have to write 2a sine n pi x by 2a. So you can get the function 1 by a here, sine n pi x by a. So you can get the normalization constant direct here, but the actual method is psi star psi is equal to 1. So you can do it as an exercise. So also the very important point here we will discuss is after equation 12, that is our fourth bullet. Also the wave functions corresponding to odd wave functions are symmetric, like odd values are 1 3 5. So the equations corresponding to this is are symmetric. And what I want to say, that like say symmetric, what I want to say, that is symmetric, that is n is equal to 1. N is equal to 1 is odd and it is symmetric. Why? Because the corresponding eigenfunction is cos, and cos of minus theta is equal to cos theta. One can take an analogy with this. So this is not the proper physics I am describing, that cos of minus theta is equal to cos theta is not the physics, it's the maths. So but you can take an analogy of this. So this is a symmetric cos theta is even function symmetric, so the values the quantum numbers corresponding to this will be symmetric. So you can see from the graph also it is symmetric. What is the probability in the left hand side is the probability in the right hand side. So basically n is equal to 2 is not symmetric, it is even quantum number, and the corresponding wave function is on psi. So sine of minus theta is equal to minus sin theta. So basically you can do this. So here come up with symmetric and anti-symmetric function. What is symmetric? You can also do this, that is, if psi of x is equal to, I change it with psi minus x, then it will become minus psi x and it is odd. If it is psi x is equal to psi minus x, then if you get psi x, then it is even wave function, even function. This is odd and even case, which I have told you. So this is, now we will go to our next slide. So here we will talk about the your ground state energy. So if we will give the value 1 in the previous equations, then you will get the ground state energy and corresponding eigenfunction, which you can see equation number 13. See, basically any particle confined in a box must have certain minimum energy, which is called 0 point energy, which is in accordance with the uncertainty principle, that if since uncertainty of order a in the width a in position implies an uncertainty of order a, it is in accordance with the uncertainty principle, like h cut by 2a, momentum will come, like I can tell you this, like uncertainty principle we have studied. Del x del p h cut by 2. Okay, so if I write momentum, it should be h cut by 2 delta x. So you can see here h cut by, will get the uncertainty of order h by 2a in momentum. Okay, h cut by 2a in momentum, which in terms give energy, minimum energy of h cut by square 8ma square. So this is in accordance with the uncertainty principle. So this should be minimum energy that which will show that there is probability of finding the particle in a box. So now we will talk about nodes. General theorem about nodes is, if the ground state starts from n is equal to 1, the number of nodes is given by n minus 1, and if the ground state starts from n is equal to 0, then the number of nodes is given by n. So here our ground state starts from n is equal to 1, so the number of nodes is n minus 1. So ground state has zero energy, ground state has n is equal to 1, so it has 0 nodes, 1 minus 1 is equal to 0. First excited state, that is n is equal to 2, has 1 node, and n is equal to 3 had 2 nodes, that is 2 minus 1 is equal to 1, and 3 minus 1 is equal to 2. So n is equal to 3 has 2 nodes. So what are nodes is that probability density. Basically in loose term we can say the probability of finding the particle is 0, but it is not technically correct, because probability can be 0 on another phases also, but here the probability density is 0. Now what are nodes? We can see it clearly here. Nodes, probability density is 0. See, when I talk about nodes, you don't count boundaries, so here node is 0 and here node is 1. Node is here, mark it with green, that point is the probability density is 0 here, and here are 2 nodes like n minus 1, so it is n is equal to 3, so 3 minus 1 is equal to 2, so there are 2 nodes where the probability density is 0. So in this video This is my last slide. So I've spoke here about particle in a box and derivation of Schrödinger equation, and I end up with this video here only. So in my next video I will come up with some questions here of in particle in a box and on the Schrödinger equation. So thank you.